Greetings everyone. The project we're working on is the CSTR continuously stirred tank reactor model of a jacketed non-adiabatic tank reactor. It is perfectly mixed with a single first-order exothermic and irreversible reaction from reactant A to product B. Over here we have two equations developed from the material balance dCA over dt. Ca stands for the concentration of reactant A, as well as the second equation dt over dt, the temperature, change in temperature over time. The reaction equation is equal to 3Ca, and over here we have general information about the components we have and the variables. Moreover, information about the values of the variables are very important for the equations we're going to be using in Simulink. Starting out, I'm going to create a new Simulink file and open the library in order to enter all the blocks needed. I'm going to start with commonly used blocks and enter the three constants that are needed for the first equation, dCA over dt. First, I'll just arrange them, and I'll go back to the equation to see. So our first three variables are f over v and the c feed. So I'll start by defining each one of them. F is defined as 200 meters cubed per hour. They're all in the SI unit, so I wouldn't have to convert anything. So 200. I'll rename this to F and this to V. The volume is 380 meters cubed. Double click and 380. For the third constant, it is the C feed, which is 10 moles per meters cubed. 10. Now I'm just going to go back to the equation. So it's the volumetric flow rate divided with the volume. So I'm going to add a new function here. I'm going to be needing a divide function. This divide function, the block, I'm going to enter the first inlet of f to multiply, and v I want it to be 1 over v, therefore I'm going to put it for the divide. As you can see here, this is multiplication and division. I'm going to go back to the equation. F over v is then multiplied by c feed minus ca. Ca is the one that we're going to be needing. Therefore, I'm just going to create first the integration function. I'm going to go back to commonly used blocks and look for the integrator. To put the integrator, I'm going to also be needing the scope that views. So I'm going to call this CA. Okay, and the integrator to be dCA over dt. The initial condition of the concentration is going to be entered here. It is equal to 100. I'm going to go back to the equation. This is C feed minus CA. So I'm going to be needing a sum block from here. So I'm going to check first the signs. C feed is positive while CA should be negative. I'm going to right click to rotate it. Oops. Yeah. Right click. Okay, perfect. So this is going to the positive C feed, and this is over here. So this is C feed minus CA. And this one is going to go to be multiplied by F over V. So I'm just going to create another multiplication block. It's called a product block. We're going to look for over here, yeah. So this goes to the first one. So this is, I'm just gonna define this one as, name the stream as C feed minus CA. And this one to be F over V. Before I forget, I'm just gonna arrange all these. Okay, so the product of F over V times C feed minus CA is going to be subtracted by the reaction R. R over here is defined as 3CA. So I'm gonna open the library and add another product as well as a sum. So the second inlet to this should be negative. Hold on. This is minus R. The outlet is going to go to the integrator, and the first product is here, while the second one is over here. For the product, I'm going to be multiplying over here. It's 3CA. So I'm going to create a constant block here to be 3, and multiplied by CA. So there you have it. That's the first equation we have. This is dCA over dt equals to F over V C feed minus CA all minus R. Sorry. I'm just gonna play this, see if this works, and this should be a decreasing function over here. It's shown because the concentration of A decreases over time while the concentration of B increases. Okay, then we're gonna move on to the second equation. It's the energy balance, d temperature over d time. As you can see here, F over V is common, therefore I'm gonna be taking the same function, and I'll first do the integrator. And the scope. So I'm going to take the F of V. Instead of creating new ones, I'm just going to take it there. All multiplied by T feed minus T. So I'm going to create a new constant, T feed. I'll just rotate this downwards. Call it T feed. To see the temperature, T feed is at 250 kelvins. So the value here is 250. So 250 minus T. So I'm going to be inhaling the sum. Okay, so this is, just before I forget calling it, this is d temperature over d time, and this is T. So this is T feed minus the T, changing the second sign into minus, and this is then multiplied by F over V. So I'm going to be taking it, I'm going to be creating a new product. As you can just copy this one, Control C and Control V, put it over here. So this is the first multiplication, and the second multiplication comes from here. It can get messy, so just arrange them again. Okay, so therefore now we have F over V, and this is T feed minus temperature. So I've done the first part of the equation, and now I'm going to be adding a sum of Q generated over rho Cp times V. This is the sum. So now we have four actually constants. I'll go to the library, create 4. Back, or I could just easily Control C and V. Okay, so the first constant is Q. Q generated is equal to 30. So Q gen is 30. Second one is raw, which is 600 kilograms per meters cube. I can call it density. 600, and as you see here, Cp is 2 and the volume is 380. So now we're gonna be needing to multiply these three variables, density and Cp and the volume. So I'm gonna create a new product block over here. The product block over here has 2 inlets, but we're gonna be needing 3 inlets, so I'm gonna change it to the number of inputs 3. So density multiplied by the Cp multiplied by volume should all then be divided by the Q generation. So I'm just going to copy this one. Zoomed out. So the output of here should be divided, and the Q generation. Okay, so now we have Q generated over density times Cp times V, which is this one. This part should be added to the first part we already did. I'm just going to change the signs to both positive. First inlet is from the product, and the second one. And there you have it. I connected the addition of the first part of the equation to the Q generated over density and CPV into the dt over dt to find the temperature. I'm just going to play first. And this is the increase in temperature going on inside the equation. As you can see here, these are the two equations we just modeled, dCA over dt and dt over dt.